second session of today's program, and topic is blockchain. And there are 3 talks. The first talk being Ophelimos, combinatorial optimization via proof of useful work. Matthias Fitzi will be giving the talk. Please go ahead.
Okay, this is joint work with Angelos Giayas, Yorgos Panayotakos, and Alexandros. The purpose of a permissionless blockchain is to maintain a transaction ledger by maintaining an ever-growing list of transactions. And we want to achieve that in a way that that maintenance of that ledger is totally public, open to the public. But that now introduces the problem that the adversary might execute the so-called Sybil attack, wherein he tries to assume many different identities and try to overwhelm his power on the system like that. And that's why we introduce a resource-based lottery, where the participants in the system have to prove possession of a resource in order to qualify for such a ledger update. The most prominent example of such a blockchain, of course, is Nakamoto's Bitcoin, which is based on proof of work, which is originates from Dworkin Nauer, and the term was coined by Jacobson and Jules. And there the idea is that you challenge a client who wants to do something, and upon that challenge he has to solve a moderately hard puzzle in order to qualify to operate on that challenge. Now the drawback of that is that this leads to energy waste, because these proof of works serve nothing else than basically maintaining the ledger. And even more so, the energy waste that the system basically requires scales with the security of the system. So the more you want the system to be secure, the more computing power has to be dedicated to the system. And as of now, Bitcoin actually has the carbon footprint of Greece, although that pollution has the advantage that it typically stays in Athens, so it doesn't have a global impact. But there are alternatives for that, and one of them is proof of space, devised by Dzimbowski, Faust, Kolmogorov, and Piechak, where you just exchange this resource of computing power against data storage. Another alternative is to apply proof of stake, such as Snow White, Algorand, or Ouroboros. But such systems are based on different setup assumptions. So the idea of proof of stake is that you can execute influence on the system depending on the number of coins you own in the system. And then the third one is proof of useful work, which this work is about. So what is proof of useful work? We just execute this proof of work, but we are trying to repurpose this work for a computation that is of real world benefit. So there is previous work on this. There is this Primecoin blockchain by King, which basically consists of, or the useful work there consists of computing new large prime numbers. And this application is maybe not so useful after all. And also the protocol is not proven secure. There is work on resource efficient mining by Zhang, Eyal, Escriva, Jules, and Van Renesse. But this is actually a good solution, but it is based on trusted hardware. And there is a whole line about distributed problem solving, but all these works basically work without the formal analysis. And actually, there is a folklore belief in the Bitcoin community that actually the work you invest into a proof of work system has to be essentially useless for anything else in order to achieve blockchain security. And basically, this belief is founded on the following dilemma, basically, that if you want the computation to be truly useful, you'll have to, that means using real-world problems, you have to be careful that the adversary does not inject problem instances of which he already knows the solution. And so on the other hand, if you want it to be secure, maybe it's better to pose totally useless pseudorandom instances. We solve this dilemma by giving a proof of blockchain protocol, which solves hard optimization problems. And by that, I mean real-world client problems, such as problems in logistics or scheduling problems or SOT solving. We give a formal security proof in the random oracle model. We achieve up to 1/2 of adversarial computing power, security against such an adversary, where we assume the adversary to be weak in the sense that he has no speed up computing the useful computation in comparison to the honest participants. But then the security can downgrade to 1/3, only tolerating 1/3 of the adversarial computing power, assuming a strong adversary, where we assume that the adversary can basically compute the useful work for free. And then we also analyze the usefulness rate of this protocol, by which we mean the rate of computation a miner really spends on the useful computation, rather than do other computations that may or may not be necessary to achieve such a proof of useful work query. And so if the runtime distribution of the useful work algorithm is well concentrated around the mean, we can actually achieve usefulness 1, assuming the weak adversary above that has no speed up for the useful work. We achieve roughly 1/2 usefulness for the same kind of characteristics we need for the useful work algorithm, but under assumption of the strong adversary that basically does not compute the useful work. But then I also have to mention that the usefulness can deteriorate quickly if you do bad choices of your useful work algorithm. So the right choice here is really crucial. And we achieve this without using any trusted hardware or third parties assumptions. Okay. So let me briefly sketch what happens in POF, in standard proof of work in Bitcoin. In order to mine a block, you just repeatedly try to achieve to obtain the longest chain of blocks, and then you try to append this longest chain by a new block you manufacture yourself, and then you hash this block. And then you see whether the hash value is below a certain threshold, and that will allow you to publish the block. Otherwise, you just vary a counter in the block until you hit that hash value below the target. And then it's an essential observation here, basically, for this work step we apply in this loop, is that this evaluation, in this case of this hash function, should be relatively fast, because otherwise you'll obtain bad characteristics of your blockchain protocol. But this now can be offset by regulating this threshold such that you only have a moderately hard success probability. So when trying to inject our useful work here now, we have to make the following observation. Basically, we require that the whole useful work problem instance we are working on is non-trivial. And that's because otherwise clients would not be incentivized to delegate computation to the blockchain, rather solve them quickly at home. And so, but in order to keep the essential property of above, that inside this loop, the computation spend should not be too high, we actually need a useful work algorithm that is decomposable in more or less little uniform steps. Right? And so what's a good class of algorithms to fit this useful work we want to inject here is local statistic search, stochastic local search. And so let me briefly sketch this. SLS is applied to computationally hard optimization problems like traveling salesman, for which efficient deterministic algorithms are not known. And so how does it work? We have this state space of possible solution. We map it to an objective function, judging the quality of such a solution. And then we just perform a random walk in this state space with the goal to find the state that minimizes the objective function. And we do that by repetitive application of the so-called exploration step that goes to one state and then explores the neighborhood of that state, and then reveals a new state, S prime, and so on and so on. And then we're trying to find a good solution by involving a certain termination criteria for that search. Maybe let me mention that SLS is highly relevant in practice. It's used in a lot of real economy logistics problem. The NFL schedule, sports schedule, is calculated by using SLS, and it's also good for site solving. To make our SLS fit for our proof of useful work, we transform it in what we call doubly parallel local search. And that is, when the problem is initialized, we actually spread it into operating multiple threads, state update threads, in contrast to how it looked before. And that would be basically one source of parallelism. And the reason for that is that we don't want too many miners to try to explore on the same state, because that would cause overhead. And then when you're ready, or when you're trying to update this SLS computation, then inside your algorithm trying to find the block, you execute many instances of this end computation on the state you're focusing in on your specific thread. And then from all these executions, you try to pick, or you pick and publish the best solution together with your block and transactions. And so this is the second level of parallelism we have here. Yeah, and so let me try to give a stepwise construction that leads from standard proof of work to our protocol for proof of useful work. So in standard Bitcoin, we have this block we hash against the target T, and then we start varying the pointer until we're successful. And as soon as we are below that threshold T, we're allowed to publish the block. And so in order to inject this useful exploration step here, we prevent this hash by a hash followed by the exploration step, where the purpose of the hash, the first hash, is just to provide a seed for the computation of M that leads to a state S prime, and then we still hash this state S prime together with the seed to see whether the hash result is below the target or some target T. And this is important because we want to decouple block success from success of finding a good solution, a good state solution. And then so instead of just hashing, you continuously repeat this HMH cycle while keeping the best state as best you've found so far. And then once you hit that threshold, you publish your block together with the winning state S prime. to prove that you act as a proof of useful work, basically. And with this, you deliver your best solution you found, which then will be used for the SLS update. And now we still have a problem with this because we have a lot of nodes in the system. And that means we cannot afford that every node in the system is going to verify the proof of useful work by repeating this whole computation of M, because that would cause an incredible amount of overhead. So what we do here, oh no, sorry, I was speaking ahead. So we have to do something different first, and that's we have to define against grinding attacks. So we may have some variance in the complexity of computing M. And so what the adversary might try to do is that if he has computed the first hash, he might not like the seed he got because he knows he now has to evaluate a very hard instance of the same computation. And so he might actually grind for easy cherry picking of M executions by just repeating the hash and not actually executing the M computation. Yeah, and so for that, we actually now require to repeat hashing before the useful work step until you reach the hash value below a certain threshold T1. And we set the T1 such that the expected number of steps you have to do in order to be successful to proceed to the M stage, those steps must be more than the worst case complexity of M. So there is no advantage for the adversary in grinding for other M instances. And the observation here is that this, this now introduces useless work again, right? Because now you repeat hashing. And so the observation here, of course, is that this heavily depends on how well formed your algorithm M is. And that basically the trade-off here is that less concentrated the distribution of runtime executing M is, the more you have to compensate it by useless hashing. Okay, now we are here where I jumped to before, unfortunately. So to minimize verification time by the other nodes, because we have to account that towards the usefulness of the system, we now just require a successful miner to publish the block not only together with these witnesses S best and S prime, but also a snark that he computed these S's correctly. Proof for S prime to prove that this indeed constitutes a proof of useful work, and S best to make sure that he cannot smuggle any bad update into the system. A note here that the loss here, computing the snarks again is kind of unuseful work, right? Note here that we only publish or compute and publish 2 snarks, while in the loop here, we compute many invocations of M. So the computation of snark will not substantially decrease the usefulness. Okay, so that's the final picture of the construction. And for the analysis of this, we need to make an assumption, and we base it on the following definition, which is we say that the exploration algorithm M is W epsilon K moderately hard. If the following holds, the adversary succeeds in the following security game with negligible probability in the security parameter. And his task is to attempt to create some M in order polynomial of the security parameter proof of useful work queries, but in time less than 1 minus epsilon time M times W, where W is the worst case complexity of M. So you can see this epsilon here as the adversary's advantage in computing the useful work. And so what we do for our analysis, we assume that our M exploration algorithm M is W epsilon K moderately hard, and we obtain non-trivial results for any such epsilon, even for epsilon equals 1. Okay, so we now deal with a slight difficulty as compared to standard POW for the standard analysis techniques you would want to apply to such a system. And we observed that as POW mining was a totally stateless process. Now we are in a stateful process here, because now basically the miners operate in this along this Markov chain, depending on how the thresholds are set, etc. And so this could be harmful because this could put the miners into correlation. And we cannot afford this because correlation of mining successes basically invalidates blockchain security, because basically the honest parties will interfere with each other trying to make progress updating the ledger. And so and especially the problem here is as soon as a new block is published, everybody would, of course, by the standard rule, jump back to the pre-hash state where you start with the hashing before M. And then this would completely correlate all miners in the system. So this is dangerous to have. And for that, we introduced the following rule for mining. And that is basically that you do not ask for immediate restarts. If you see a newer longest chain, so in standard POW, as soon as you would see a newer longer chain, you would immediately adapt to that chain and produce a new block. And our rule now here is that you don't do that immediately, but that you basically finish your initial, your H cycle you're currently in. And then if you fail here and come back, then you're ready to adopt the newest longest chain. The good news here is that basically, with respect to this Markov chain, the miners they correlate fast, and that gives us the hope that we can solve or give the analysis applying standard techniques that have already been around. And so we show that by giving a simple coupling argument. So we assume that all the miners start in pre-hash state at the beginning, and compare it to a system where the miners are already independently distributed with respect to the stationary distribution of that Markov chain. And then we basically play a Gedanken experiment where we let those miners proceed in both systems. So we have the M minus P that's not in pre-hash, and the S1 to SM that are independently distributed. And then we see, we just apply one update according to the Markov chain after another, progressing in this state. And then we look at the situation when a pair of such miners, PI and SI, meet in the chain. And then we can observe that since now they are in the same chain, same state, and are based on the same update function, that they will now move in sync in the future. And by that, we can show that the distributions of those random variables actually come together, close together exponentially fast. And so we do that by coupling argument, assuming that or observing that two miners, or the two miners P1 and S1 will actually land within any period of E steps, both will land in the pre-hash state. And thus we can observe both particles within these, or both miners within this period E. And then we can look at the first miner that appears in pre-hash, and then the second miner that appears in pre-hash. and then as long, or if the first minor that arrives there stays in pre-hash until the second one arrives, then we have a coupling, and then both minors will behave the same. And so we can estimate this by this probability by 1 minus p1 to the e, and assuming a linear snark prover, we get together with the condition on p1, we get that this is larger than 1 minus 1 divided by w to some constant times w, which is a constant. And now by a standard argument, we can conclude that after LE such steps, the total variation distance between the distributions is exponentially slow. Is exponentially small by L. So this now allows us to analyze the security of the protocol by using the fact that the minor states are close to independent pretty quickly. And so we can adapt the existing machinery, which I spare you from, but I'll just give you an intuition here. We achieve 1/3 of security against 1/3 of adversarial computing power if the adversary is strong. That's he has advantage 1 in computing the exploration step M. And if we do make a strong assumption about the adversary, then we can tolerate the same as Bitcoin. That's half of adversarial computing power. And then we also give a short usefulness intuition. So usefulness U is the rate at which the miners perform useful work. And if the worst case complexity of M is roughly the same as the average complexity of M, we have usefulness 1/2, because the miners spend 1/2 of their time doing this pre-hash cycle. But then if we add the assumption of a weak adversary that has no advantage, actually usefulness can be 1. So let me compute. We devised a proof of useful work blockchain protocol that allows to solve real-world client problems. We analyzed the security in the random oracle model, demonstrating that the system tolerates between 1/3 and 1/2 of adversarial computer power, depending on the assumptions on the adversary. And then usefulness can range between 1/2 and 1 for basically concentrated exploration algorithms M. And thus we reduce or would be theoretically, at least if people would adopt this, we would be able to substantially reduce the pollution created by proof of work blockchains. Yes.
All right. Okay. We have time for one very quick question. Yehuda.
Something that people would issue problems and then summary chosen from them, and would that also, would they pay transactions that as well?
Yeah, so you would basically have a problem market where clients can post their instances to the blockchain. Of course, they must conform to certain rules, right? And then you can schedule the mining by maybe picking multiple of those problems. And then, of course, also the client can submit some fees, so you can drive the incentives also by the fees.
Okay, let's thank Matthias again.
Thanks a lot.
And we're going to move now to the second talk of this session. The title is Practical, Statistically Sound Proofs of Exponentiation in Any Group. And the speaker will be Charlotte Hoffman, whenever she's ready with the microphone.
We have
Okay,
no
hi.
sound.
So I'm Charlotte, and I'm going to tell you about practical statistically sound proofs of exponentiation in any group. This is joint work with Pavel Hubacek, Chetan Kamat, Karen Klein, and Krzysztof Pieczak. In a proof of exponentiation, we have a prover and a verifier. And they both get as input some tuple xq, t, y. And now the prover claims that the result of the exponentiation x to the q to the t equals y in some group G. But the verifier doesn't trust the prover. So how can the verifier efficiently check that this is actually the correct result? Well, if the group order is known, then this is easy. The verifier can do exactly the same as the prover. They can both reduce the exponent, modulo the group order, and then raise x to that value. However, if the group order is not known, we don't know of any significantly faster way to compute the result than to perform t sequential exponentiations. So that's what the prover does, but we want the verifier to be more efficient than t. And so to this end, the prover sends a proof of exponentiation to the verifier, or POE, to prove the correctness of the result. And here the cost of computing and verifying the proof is much less than t. Now, what are the applications of such POEs? The most well-known applications are verifiable delay functions. These are functions that are verifiable. So given a proof, everyone can efficiently and also soundly verify the correctness of the result. They satisfy the delay property, which means they cannot be computed faster than a given time parameter t, even given parallelization. And finally, they are functions, so the output is unique. VDS were first introduced by Bonnet et al. In 2018, and then shortly afterwards, Pieczak and Wesolowski gave the first practical constructions. They are based on repeated squaring and then sending POEs. Another more recent application are time and space efficient arguments for NP by Block et al. Here, POEs are used as building blocks in constructing polynomial commitment schemes. All right, so this is the plan for the talk. First, we're going to look at some existing POE constructions and their properties. And then afterwards, I'll give you a technical overview of our POE. But first, I want to define interactive protocols because all of the proofs we're going to see will be interactive. So in an interactive protocol, again, we have the prover and the verifier. They both get as input some statement X, and then the prover also gets a witness or just more computational power than the verifier. And then they engage in some interaction, so they send messages back and forth. And then afterwards, the verifier outputs accept or reject. And we want interactive protocols to satisfy two properties. The first one is correctness. So if the statement is true, we want the verifier to accept with probability 1. The other one is soundness. If the statement is false, then the verifier should reject with high probability. And there are two different notions of soundness that we consider. The first one is statistical soundness, which means that a potentially cheating prover is computationally unbounded. The second one is computational soundness, where the cheating prover can only perform polynomial computations. Now let's look at the POEs that are already existing. Note that this is the statement we want to prove, x to the q to the t equals y. So there's Wesolowski's POE, which is very short. It only consists of one group element. However, soundness is only computational, and it relies on the adaptive root assumption, which is a quite novel assumption and not that well studied. Then we have Pieczak's protocol, which is a bit longer. So here the proof size is log t. However, this POE is statistically sound in some groups, and in other groups, it can be computationally sound, relying on the low order assumption. Note that there's a reduction from the adaptive root assumption to the low order assumption. So if security of Pieczak's protocol is broken, then also soundness of Wesolowski's protocol is broken, but not the other way around. Finally, there's a construction by Block et al., which can be seen as a clever parallel repetition of Pieczak's protocol. Due to this repetition, the proof size increases to lambda times log t group elements, where lambda is some statistical security parameter. However, this POE has the advantage that it is statistically sound in any group. Now, our contribution is that we construct a statistically sound POE that reduces the proof size of blockade I by almost 1 order of magnitude for Q of a special form. And we will later see that in the applications we consider, choosing Q of this form is not a restriction. Okay, so we have seen that we can get stronger soundness guarantees by increasing the proof size. So the first natural question to ask is, why do we even care? Like, why do we need statistical soundness for POEs? And there are several reasons for this. First one is that in the application of the polynomial commitments by blockade I, here we need statistically sound POEs to get statistical knowledge soundness of the commitment. But also in VDFs, it can be useful because if you have a statistically sound POE, then soundness holds even if the group order is known by the prover. This is important, for example, in settings where the group is sampled by certain parties, because then the parties know the group order, but they still cannot come up with a false proof. Another reason is that if you want to use the POE in class groups, here the low order assumption is not very well studied and understood. Okay, but we have seen that there is already one very efficient POE, which is sound in some groups, which is Pichak's POE. However, these groups require safe primes. So you need to sample safe prime numbers. And then in a lot of applications, you also need to prove that the modulus is a product of safe prime numbers. And those two things are very expensive. So if you have a statistically sound POE in any group, then you don't need to do that work at all. Okay, so let's start with our technical overview. First, I'm going to show you the POE construction of blockade I, because this is the construction that our work builds on. And then I will show you our work, how we reduce the complexity. Okay, let's look at one round of blockade I. So this is the picture we have already seen. So let's have a closer look. The proof and verifier get as instances lambda many statements of this form, xi to the q to the t equals yi. And then in the first round, so the first message of the prover is the prover sends lambda many group elements of this form, xi to the q to the t over 2. We sometimes call these elements midpoint because in the exponentiation, they're in the middle of xi and yi. Now, note that by sending this group element, the prover implicitly splits up the first claim into 2 smaller claims. So one of the claims is that this is that gi is the correct group element when you do this exponentiation. And then the second claim is that if you take the group element and raise it to the power q to the t over 2, then you get the element yi, which is the claim of the initial statement. And it is straightforward to show that if at least one of the initial instances is wrong, then also one of the two new statements is wrong. Okay, so we have made some progress here because we have reduced the exponent from q to the t to q to the t over 2. However, we have also doubled the number of instances, the number of statements. So, and because this protocol is recursive, we cannot afford to double the number of statements in every round. And so we need some way to recombine those 2 lambda statements back together into lambda, such that if at least one of the 2 lambda statements is wrong, also one of the new lambda statements is wrong. And we will now take a look at how this is solved in blockade I. So let's say the prover and verifier now have these 2 lambda statements of this form. And the goal is to reduce the number of statements to lambda. This is done as follows. First, the verifier sends a random bit string of size 2 to the lambda. And then both the verifier and the prover compute a random subset product, where the statement is in this product if and only if the corresponding bit equals 1. And then the first thing we can note is that if at least one of the initial statements is wrong, then the new statement is wrong with probability at least 1/2. So let's say, for example, statement number k is a wrong statement, then the corresponding bit rk will be equal to 1 with probability 1/2. And if it's equal to 1, the statement is in the product, and then also the new claim is wrong. Now, if the proof and verifier repeat this process lambda many times with different randomness, then we can say that at least one of the new lambda statements is wrong with probability at least 1 minus 2 to the minus lambda. And so if we choose lambda to be a statistical security parameter, then this probability is overwhelming and we have soundness. However, this is also the reason why the proof size increases by this multiplicative factor of lambda. So the goal of our work is to reduce the number of repetitions that the verifier and prover do. And so let's have a look at the first step of our construction. So recall that in blockade I, the probability that one new statement is wrong is lower bounded by 1/2. Because, for example, if only one of the instances is wrong, then it's in the new claim with probability 1/2, because the randomness is only 0 or 1. So a straightforward idea would be to just increase the randomness space, because then every statement contributes to the node product. So you take statements and raise the statements to small coins, and then you multiply them all together. And then you could hope that this increases the probability that the new statement is wrong. Unfortunately, this is not the case. So the lower bound of this probability is still 1/2. And why is this? Well, this is due to low order elements. In the context of VDFs, this was first described by Bonnet et al. But already in 2000, Boyd and Pawlowski showed that low order elements can mess up random batching. So let's see why. Let's say in statement K, the prover cheats with some bad element alpha. So the prover takes a correct claim and then multiplies it by a wrong element alpha. We sometimes call this element the bad element. Now, if the prover is lucky and the order of alpha divides the random coin, then what happens? Well, when both the prover and the verifier raise a statement to this coin, then they also raise the bad element to this coin. So they raise the bad element to a multiple of its order, which means, which means it just vanishes. And so the statement you end up with is correct. The probability that the order of alpha divides RK is 1 divided by the order of alpha. So in the worst case, if the element only has order 2, we again have the probability 1/2 that the new statement actually becomes correct. Okay, so far we have not increased the probability, but we have now seen that we only need to take care of the low order elements. So let's look at so let's first change the randomness of the protocol, increase the randomness space, and then look at the second step. Now we're going to look at the instances that the prover and the verifier get. So for this, we define this exponent Q to be of a special form. So we let Q be the product of all small prime numbers up to a certain bound B. And then we also define a constant as log T times log B. But for the purpose of this talk, you can always just think of C as being large enough. And now we change the instances that the prover and the verifier get. So instead of proving the claim x to the q to the t, we now change the exponent to q to the t minus c. Then we let the prover prove these instances in some interactive protocol that is not really interesting to us right now. And then after this interactive phase, the verifier performs these final exponentiations themselves. So for all I and lambda, the verifier takes the claimed result, yi tilde, raises it to the power q to the c, and then obtains the result the verifier is actually interested in, namely yi, which is the result of the exponentiation with q to the t. Now, why is this helpful for us? Again, let's assume the prover cheats in statement K, multiplies the statement with a bad element alpha. Now, if this alpha has low order, then we know now that the order of alpha divides q to the c, because this is exactly how we've chosen q. Q is the product of all small prime numbers, and c is large enough. So, so what happens when the verifier performs this final exponentiation? Well, the verifier raises the bad element by q to the c, and because this is a multiple of its order, the element vanishes. And so what the verifier ends up with is the correct result, yk. So even if the prover cheats with a low order element in this intermediate result with the exponent q to the t minus c, the verifier does not care about that, because all the verifier is interested in is the final result with the exponent q to the t. And this is what the verifier gets, even if the prover cheats with some low order elements. And okay, yeah, so this is the result of the exponentiation. And this allows us to reduce the proof size of blockade I from lambda times log t elements to lambda times log t divided by log b. Okay, so let's recap. How does our basic protocol look like? So we define this Q of a special form, and then we change the instances. So we let the prover only prove statements for exponent Q to the T minus C. Then we reduce the number of elements and statements the verifier and prover prove to rho, which we define as lambda divided by log B. This means that if the prover cheats with low order elements, the verifier might not catch it in the interactive phase, because we have now reduced the number of repetitions. However, the verifier then performs the final exponentiation and still ends up with the true result of the exponentiation with q to the t. Okay, so yeah, to conclude, why is the statistical sound? Where if the prover cheats with element alpha, and if the order of alpha divides q to the c, then the verifier obtains the correct result, and we're happy. If the order of alpha does not divide q to the c, by our definition of q, then alpha has sufficiently large order. And so we know that the verifier will reject after the interactive phase with high probability. Okay, now let me say some words on the parameters q and b. Because note that if you define q like this, we let q be the product of all small prime numbers, then if we increase the bound b, of course, q increases exponentially. So q will be quite large. However, in the application we consider, this is actually to our advantage, because in blockade I, you need a very large q to ensure soundness of the polynomial commitment anyways. So in particular, q has to be much larger than 2 to the n times poly lambda, where n is the size of the input. Also in VDFs, you can just, if the q is very large, then you can just adjust the cost of the initial exponentiation by adjusting the time parameter t. So we will then choose t a little bit smaller. So let's look at an example with numbers. Let's set the statistical security parameter to be 80, and t is 2 to the 32 in practice. And then let's choose the bound b to be the prime number 521. Then q is approximately of this size, 2 to the 703. And then we can do the computation and see that the proof size drops from 655 to 74 kilobytes. So to sum up, let's look at a comparison of the PREs that we know. We're going to look at the cost of verifying lambda many PREs, because this is what's needed in the application of blockade I. So we have seen that the PREs of Veselovsky and Piechak are very, very efficient. However, they are not statistically sound in every group. The first PRE that's statistically sound in every group is the one by blockade I. However, the proof size increases to lambda times log t. Now, we have seen in this talk that with our basic protocol, we can reduce the proof size to lambda times log t divided by log b. However, what we have not seen is that by doing so, the verifier's complexity increases, because now the final exponentiations the verifier has to perform are a bit more costly. However, what we show in our paper is that we can handle this as well by recursing on the claims with exponent q to the c, and then batching claims together. And yeah, doing so, we can also reduce the verifier's complexity until it's lower than the one in blockade I. And yeah, this is all I wanted to say. And now I'm happy to take questions.
All right, so we do have time for questions. Yes, please go ahead in the back.
Right. Okay, wait, let's go back. Okay.
Just also repeat the question perhaps for the Zoom.
Right, okay.
call.
So the question was if I can talk more about the parameter C, and in which cases you would choose C bigger in comparison to choosing the bound B to be bigger. So we usually want C to be small because of the final exponentiation. So C is the number. Okay, so when the verifier computes the final exponentiation with Q to the C, it has to perform C exponentiations, right? So we want to choose C as small as possible. However, okay, what we have not seen here is that if the order of the bad element is a small prime power, then the prover does not need to get rid of this bad element in one go, but it can just reduce the order of the element in every round. It can just lose some factors of 2, for example. And so this is why we need C to be at least this big. So at least log T times log B, such that again, so the probability of the bad event, which is that it loses too many factors of too many powers of 2, is again 1 over B. Right. So yeah, but in general, you want to choose C small.
We have time for one more question. Yeah, please go ahead.
So no, the group order does not need to be known by anyone. However, so here we look just at the proof of exponentiation, right? And so this is sound even if the proof order is known. Here we don't need any assumption. Of course, if you then want to use it in a verifiable delay function, for the delay property, you will need the assumption that the group order is unknown. But the proof is sound, yeah, statistically sound. Then you don't have the delay property, right? But right, so this is for VDFs, but in the application of block et al, you don't need the delay property. You just want to prove a very large exponentiation.
Okay, so let's thank the speaker again. Thank you, Charlotte.
Thanks.
And now we're getting ready for the third and final talk of this session, of the blockchain session. The title is Formalizing Delayed Adaptive Corruptions and the Security of Flooding Networks. And the talk will be given by Soren Eller Thompson, who is just setting up now his microphone and slides.
All right, so hi everyone. My name is Søren Thomsen, and I'll be presenting the work Formalizing Delayed Adaptive Corruptions and the Security of Flooding Networks. So this is joint work with Christian Matt among the audience and my supervisor Jesper Buus Nielsen. So since we are at the blockchain session of crypto, I thought I would motivate this work using the example of Nakamoto-style blockchain. All right, yeah. So Nakamoto-style blockchain is a type of protocol where a group of parties participate in some lottery, which can be instantiated as proof of work, proof of space, proof of maybe useful work, etc. So the way this type of protocol works is that parties build a total order using this lottery to take turns on whom that are allowed to extend this total order. So for example, if Alice wins the lottery, well, then she will be the first one to extend the order, and she can create a block with the transactions. And afterwards, if Bob now wins the lottery, well, then he can extend the current best chain, which will be just Alice's block, and propagate this block to all the other parties in the protocol. This continues on, and there will be sort of a long chain of ordered transactions. However, what may happen is that a party wins the lottery, or if two parties wins the lottery without knowing about the previous extension of the fork of the best chain, well, then we might have a fork. There's no longer any clear total order. This can also happen sort of maliciously if, for example, Mallory, an adversary, chooses to extend something that's older than the current best chain. Well, then this doesn't create a total order either. So in order for this type of protocols to be secure, what we need is that the honest parties, they outgrow the adversarial blocks. In particular, the honest blocks which have sufficient time to propagate between parties, they need to outgrow the number of blocks created by the adversary. So this naturally induces some requirements on how we actually propagate this block in order for it to be secure. So what is typically done is to assume some kind of flooding network, which has the property that if one party, P1 for example, wins the right to create the block, now inputs this block to the flooding network, well, then there must be a bounded time delta such that if the block is input at time t, then it must be delivered to all other honest parties before time t plus delta. And such functionality has been assumed in order to prove Nakamoto-style blockchain secure. So this talk is about how to implement this functionality. All right, so now let's just look at how this functionality is implemented in practice. So again, we have the lottery, and if P1 happens to be the winner of the lottery and are allowed to extend the best chain, create a block, well, then what P1 does is to send this block out to his neighborhood. And then what this neighbor does is, well, they will send it to their neighbors and so on and so forth until all parties now know the block. This works all well and good as long as we are analyzing it against a static adversary. However, as you will soon see, this is not ideal if it's an adaptive adversary. So if we are to analyze this situation against an adaptive adversary, we need to make an assumption on the underlying channels. So we can choose to assume a non-atomic message sent channel. We can choose to assume an atomic message sent channel. Let's first assume a non-atomic message sent channel. So at the moment P1 wins, it starts sending out this block to everyone. Then, well, the adversary immediately learns this. The message or the block is leaked to the adversary, and he sees that P1 is actually sending this out. Because we are assuming non-atomic message sent channels, well, then adversary is now given the possibility to corrupt P1. And because it's non-atomic, well, then he can actually retract the message, and thereby prevent the delivery of this block to the remaining honest parties. So this gives an insecure blockchain, right? Because now no longer this blocks which have sufficient time to propagate will no longer be sufficient many to outgrow an adversary. Of course, what you could do is to assume atomic message send instead. So now the adversary can no longer do this thing of corrupting the sender of the message and thereby retracting the message which has already been sent. However, what the adversary can do is instead to corrupt the entire neighborhood, P1, and thereby prevent the delivery of this message. So this doesn't work either. Of course, assuming atomic message send, a sender could now send to all parties. Then the adversary will not have the possibility to corrupt the neighborhood, but this will also induce quite a heavy workload on P1, so therefore this is impractical. In this work, what we do is to assume a delta delayed adversary. This is a type of adversary where once the adversary chooses to corrupt a party, there will be a time delta, which will pass until the adversary effectively gains control over this party. This is not only useful for flooding networks, but this has also informally been considered by Paz and Xi for long-lived committees. So let's try to see gain some intuition for why this helps with the flooding. So, of course, if the adversary is delayed for a long time, longer than the time it takes to propagate this message to all parties, well, then it's kind of clear that he cannot really interfere, even though he tries to corrupt, because the corruption will only be effectuated afterwards. But intuitively, you can do kind of better. What we could assume is that the adversary is only delayed for the time it takes to send through a channel, plus the time to resend through a channel. So if we assume this, well, then at the moment a sender sends out the message, the adversary can now still try to corrupt this neighborhood, but it's kind of too late because it's guaranteed that these parties have sufficient time to send out to just their neighbors. Thereby, it's sort of the message has been propagated one layer further. So this won't really help an adversary. So in our work, we give two main contributions. First, we provide formal and precise semantics for delta delayed adversaries within the UC framework. And then we use this to build two instantiations of plotting networks that are secure against an adaptive adversary, delayed for the time it takes to send, plus the time it takes to resend, thus matching this intuition I gave just before. Our first instantiation has a constant neighborhood with a logarithmic diameter, and our second implementation gives a square root number of neighbors with just a constant diameter. So let's just jump right into how to define delayed adversaries within UC. So let me first give you a quick sketch of a security notion from UC. And that is that if we have a protocol which uses some ideal resource, well, then an experiment is set up where an adversary is allowed to influence the execution of this protocol using the resource. Then an environment can now play with this setup, provide inputs to the protocol, and also talk with the adversary. Now the security notion is given by defining another experiment where some ideal resource F, this is an ideal specification of the actual protocol, interacts with some dummy parties, which simply forwards all messages sent from the environment, and a simulator. This simulator can be thought of as a translation of the attack on the real protocol to an attack in the ideal specification. And then security is given as that for all such adversaries, there exists a simulator such that no environment can distinguish these two experiments. So what is interesting is how the adversary can now influence the execution of the protocol. And actually, there are no built-in semantics for this. This means that each individual machine in the protocol determines what to do when receiving something on this channel from the adversary. And this is exactly what we tap into when we define our delta delayed corruptions in UC. So what we do is that we wrap each machine in the protocol with a small wrapper called a shell. This is now what enforces some restrictions on the behavior of each individual machine when receiving something from the adversary. And similarly, well, how the simulator can now influence the ideal resources, that is also defined. That's a part of the ideal specification of such protocol. So that's defined by the ideal functionality itself. And what we do is to wrap ideal functionalities in a wrapper similar to the wrapper which we use for parties. Okay, so let me now try to tell you what these shells does. Of course, since we're talking about delays, we need that these shells somehow have access to time. And we use this notion of time from TARDIS, which was by Baum, David, Dorsley, Nielsen, and Oechsner in 2021. Okay, so now let's jump into what these shells actually do. So define what we call a delay shell for the real world for protocols, and this has a parameter delta. So it's a very simple shell. So it adds 3 additional commands to the existing code of the protocol. And the first command is a pre-corrupt command. And what the shell does is simply to note down the time when this pre-corruption is received. Then it allows corruption. And what the shell does when receiving a corruption token is to simply check if the current time is at least delta time after a pre-corruption has been received. If that is the case, it acts just as a Byzantine corruption. And if that is not the case, it simply ignores this premature corruption input. And then finally, we provide a command initialize, which has a parameter tau given to it. And this is just a way for the adversary to be able to allow to corrupt parties before the protocol execution actually starts. And actually, our wrapper for ideal functionalities has the exact same behavior, even though that the notation is slightly different. It's the exact same 3 commands. And that's the delta delayed adversaries within UC. So for this model, we are able to prove 2 theorems. And the first one is that security against a Byzantine adversary implies security against a 0 delayed adversary. The second theorem says, well, security against a fast adversary implies security against a slow adversary. This is very intuitive, but what these 2 theorems allows us to do is to say, given a protocol that is secure against a Byzantine adversary, say, for example, a Nakamoto-style blockchain, which assumes a flooding network, well, then we are able to upgrade the security to say, a delta delayed adversary. And if we are then able to prove the flooding network secure against the delta delayed adversary, then we will inherit the composition theorem from UC, and well, the entire composed protocol of this Nakamoto-style blockchain making use of the flooding network will also be secure against such adversary. Okay, so this is the model. Let me now jump to a simple protocol. This is called Ade-Reni flood. Here, Ade-Reni refers to Ade-Reni graphs, where each edge appears with an independent probability row. And our protocol is as simple as these graphs. So what the protocol says is that once I would like to send out a message, then I forward it to each party with a probability row. So if you have P1 and he wishes to send out the message, well, then he flips a coin that comes out heads with probability row for P2, and continues to flip coins for all parties and only sends to those parties where the coin comes out heads. So our main result, stated slightly informally, is that this protocol, ER flood, implements a flooding network against an adversary that is delayed for the time it takes to send, plus the time it takes to resend. This is either with a square root number of neighbors and a diameter of just 2, or a constant neighborhood and a logarithmic diameter. So let me now try to be slightly more formal about this, these theorems, this theorem. Okay, so first of all, our assumptions. So what we assume is that we have all parties connected by point-to-point channels. And this is given by some idealized resource, which we call message transfer. This has a parameter sigma, and this has a parameter delta. So the guarantee that these point-to-point channels provide is that messages input time t, they must be delivered to the recipient before time t plus delta, if the sender stays honest until some time t plus sigma. Okay, so we plot this on a timeline. What happens is, well, if some party sends a message through the channel, the message is immediately leaked to the adversary. Then there is a small time gap, sigma, where it's possible for the adversary to corrupt the party that sends the message and thereby retract the message and prevent the delivery of this message. But if the adversary does not choose to do so, then it's guaranteed that the message will be delivered at time t plus delta. So then we assume a delayed adversary naturally, and we assume that the delay of the adversary is delta plus sigma. So it takes delta plus sigma times from an adversary decides to corrupt the party until this adversary actually gains control of the party. So with this on the timeline, well, then it's ensured that it takes more time than t plus delta plus sigma until the adversary gains control. This corresponds to this time that we had before, right? That the adversary can no longer prevent the delivery of the message to the neighborhood, and these neighbors also have precisely sufficient time to send out the message and cannot be prevented in doing so. Okay, now the functionality that we implement, called flood. It has the very simple property: any message input by an honest party at time t must be delivered to all other honest parties before time t plus delta prime. Again, if we plot this on the timeline, the message is immediately leaked, and at some later point, it's guaranteed that the message is delivered. And here in particular, it's worth noting that there is no longer this time for corruption to actually corrupt a party and prevent the delivery of the message. Now sending is effectively an atomic operation. But it's also worth noting that we require it to be an honest party. this honest is defined as that the adversary has not even pre-corrupted this party that is the sender of the message. Okay, so if we say our main theorem in a bit more detail, the protocol ER_flood with this parameter rho, which describes the probability that the coin should come out head, realizes the functionality flood if we assume channels and the adversary that is delayed for sigma plus delta time. And that is either if we instantiate this rho to be the square root of a security parameter over the number of parties that are guaranteed to behave honest. This will provide us with a diameter that is just 2 times, sorry, a delivery guarantee that is just 2 times the delivery guarantee of the underlying point-to-point channels. And it's worth noting that here this theorem is proven for all number of honest parties that are guaranteed to be honest. And our second configuration is that we just instantiate rho to be the security parameter over the number of parties that are guaranteed to be honest. And then we achieve this new delivery guarantee which is just a logarithmic factor multiplied by the delay on the underlying channels. Okay, so in conclusion, this work provides a formal model for delta delayed adversaries. We provide 2 instantiations, one with a constant neighborhood and a logarithmic diameter, and one with a square root neighborhood and a constant diameter. So details can be found on ePrint, and I'm happy to take questions. Thank you for your attention.
All right, so we do have time for questions. Yeah, go ahead.
Yes,
If
exactly.
you can repeat the question.
Sorry. Yes, so the question is, can the adversary corrupt some or pre-corrupt some of the parties even before the start of the broadcast? And yes, the answer to this question is yes. This is exactly what this initialize command does. That gives the adversary the right to pre-corrupt a certain number of parties before the protocol actually starts, and that's pre-corrupt with a time decided by the adversary.
We have time for one more question. One. No, that's okay. Please, the question will be repeated. Please go ahead.
So I didn't quite get it.
Please repeat the question.
One, yeah.
So you mentioned in the non-atomic model, right? The adversary, the sender sends something, the adversary corrupts, and the message gets retracted. That's one option. It doesn't have to. Right? That message can still go. They can corrupt the sender and send different messages. Do you need messages to be retracted?
Or just to put differently, the messages are being blocked, basically. So the adversary corrupts, and then he also delays the message, so blocks also the message delivery. That's what you mean, one, right? So it's basically 2 things the adversary does, right?
That's a Hirt and Sika's paper that introduced this model, right? The non-atomic corruption model, and they illustrated that with a classical Byzantine agreement problem where the sender sends something, but then the sender gets corrupted and then sends something else. Even in that case, you violate results. So, question: do you need to retract the message, or you don't?
Okay, so for the original attack, we just need to block the message in the non-atomic multisend message, right? So there we just need to corrupt afterwards and block the message. Nothing else has to be sent in order to make this protocol insecure in that model. And in our model, if that's what you're asking, of course, well, it is possible for the adversary to see that a message is being sent You can no longer prevent the delivery of this message that is being sent through our flooding network. But of course, what he can do is to corrupt the party that has sent the message and then send a new message on the behalf of this party. Did that answer your question?
Yeah, so, and then yet another follow-up question. In a paper with Aguilas and others, we had something called resource restricted cryptography, where we have these wrappers, your shells, that can be customized to prevent different things. Are you familiar with that work?
Yeah, barely, yeah.
Could you have used that machinery to wrapper shell, right? It's the same type of thing. You parameterize it and then blocks, delays.
I'm not sure I follow. I think we should discuss later.
Yeah, so
Yeah.
wrapper is your shell, right? That blocks, controls access to a resource.
Mhm.
So that's, we had a formalism to specify those types of things.
Okay, yeah, I'm not entirely sure what direction.
Maybe let's take this conversation during the next break. That's okay, Soren,
Yeah.
and because we're almost out of time. So let's thank the speaker again.